We hear it all the time. The next big step for AI is all about one thing: scale. Bigger models, more data, a strategy that, really only the biggest players in the world can even afford. But what if that whole idea that bigger is always better is just wrong? What if you could get the same kind of sophisticated reasoning from a much smaller system and for like a fraction of the cost? Well, a small lab called Cortex Labs is claiming they've done exactly that. They've built a new AI architecture, the synthetic cortex, that's more about engineering intelligence than just brute forcing it with data. Okay, let's unpack this. Our mission today is to dive into this synthetic cortex. For you, the listener, think of this as a shortcut to understanding what could be a huge paradigm shift. It all comes down to one question: what if the structure of thought is more important than the size of the brain?
That is the core philosophical split right there. I mean, this project isn't chasing AGI hype. And it's definitely not about just finding more data to throw at the problem. Their whole focus is on modeling biological cognition, things like memory, abstraction, and especially emotion regulation. And they're building these things as explicit variables in the architecture itself.
So they're not trying to grow a brain from scratch. They're, what, installing an operating system for thought?
That's the perfect analogy. They're building this highly organized reasoning mechanism that tells an existing pre-trained model how to process information.
The implications for you, the listener, are just huge. I mean, if this works, you're talking about democratizing advanced AI. And our sources say they're moving fast. It's a 7-phase architecture, and 3 of those phases are already done, ready to be productized right now.
Exactly. The shift is already happening. It really is structural. If you look at a conventional LLM, it treats intelligence as, one single computational process, which is great for pattern matching. But Cortex Labs argues that real thinking comes from these multi-component structures, different functional layers all interacting, just like our brain has a limbic system, a cortex. They all have to work together.
That makes so much sense. So you're not replacing the big model. You're bolting on a kind of external reasoning engine.
A biologically inspired one, yes.
Mm.
And that engine defines how the thinking is structured. It's not just about predicting the next word anymore.
It's about coordination.
Precisely. An LLM on its own is incredible at statistical inference, but that's just one piece of the puzzle. The synthetic cortex is designed to be that missing integrative layer, like a real cerebral cortex where all the specialized parts come together.
And we can see that in the first few phases they're rolling out. The emotional reasoning system is the one that really jumps out.
It's fascinating.
And then there's the dynamic adapters for internal learning and latent space injection. Okay, here's where it gets really interesting. The part that sounds like it's straight out of a novel. Phase 1, emotional reasoning. They call it the limbic 2 system. They modeled the mathematical interactions of 13 different hormones and neurotransmitters.
Okay, and this is a really crucial point to be clear on. The system does not feel emotions. It is not sentient.
Wow.
It's mimicking the functional neurochemical processes that, in us, are the result of feelings. It does that by looking at the emotional content in the transformer layers, the words, the vectors, and it maps that onto what's called the valence arousal dominance model, the VAD model.
Okay, so if the AI is generating text that sounds, I don't know, like a frustrated rant, super negative, high energy, no control, the VAD model gives that a number.
Exactly, it quantifies it. And that quantitative input then triggers a synthetic release of a specific cocktail of those 13 variables.
So a frustrated rant might trigger high cortisol for stress and low serotonin for stability.
Precisely. And those resulting numbers, the levels of synthetic hormones, they become active control variables.
They're not just a log file then. They're actually doing something.
They're an active computational layer.
Yeah.
They're reshaping the model's entire latent geometry while it's thinking. They influence what it remembers, what it focuses on, its whole decision-making flow.
So they're like cognitive guardrails. Our sources say they guide the internal learning, the data injection, everything. It's like an engineered feedback loop to keep the system balanced, to maintain homeostasis.
That's the goal, cognitive balance.
But I have to ask, if the AI is suddenly stressed, high cortisol, what does that actually look like in the final text? Does it just start typing in all caps?
No, it's much more subtle. That's the structural effect on the output. Those emotional loads directly change the text generation parameters. So say the system is in a state modeled on high dopamine reward, motivation.
It's feeling good.
Right. So it increases things like numb response and temperature. It becomes more creative, more divergent. It takes more risks. But if it's in a state modeled on high cortisol stress, threat, it does the opposite. It cranks down those creative parameters and increases something like top pay up, which forces it to only pick from the most probable, safest words.
So it becomes cautious, restricted.
It's adaptive equilibrium. The AI is literally deciding if it's safe to be creative or if it needs to be strictly logical based on its internal state.
That is profound. And you mentioned those hormone pairings define specific thresholds.
They're the whole regulatory framework. Serotonin, for example, is what ensures logical stability. It stops the model from, completely changing its mind about the context in the middle of a conversation.
It keeps it on track.
And glutamate, which is key for learning in our brains, acts as the trigger for complex reasoning. It basically asks, is this problem hard enough to justify firing up the big guns, the chain of thought process? If not, don't waste the energy.
It's turning biochemistry into a kind of conceptual physics for the AI, which is a perfect segue because they're also redesigning the actual space where the AI thinks, the geometry of it all.
Yes, phase 5.
Yeah.
And this is so important to grasp. Standard LLMs, they operate in what's basically a flat Euclidean space.
A flat map.
A flat map, exactly, where the distance between 2 points is always a straight line. But that means concepts that are totally irrelevant can get dragged into the calculation just because of where they are on the map. It's not efficient. It's not how we think.
Right. Our brains work by association. We jump between related ideas, even if they seem far apart on paper. We follow the curves.
Precisely. So the solution here is a manifold. a curved surface where information is organized. Now, concepts that were distant in that flat vector space can be really close to each other along the surface of the manifold. It allows the system to focus its computation on these local neighborhoods of meaning, just like human associative thought.
So the model's core programming, the weights, they stay the same, but the path the data takes through the model is now defined by this curved surface.
And they call that implicit relation engineering. They're basically designing the laws of physics for the AI's thought process, forcing it to follow these predefined conceptual pathways.
And this connects to phase 7, right? The cultural relativity part.
It does, and it's a powerful connection.
Yeah.
Your standard LLM, it's trained on global data, so it tends to average out cultural differences. The concept of success or family gets flattened into one dominant statistical mean.
It loses all the nuance.
All of it. This architecture lets them introduce these culturally distinct semantic resonance patterns as biases along the manifold. So meaning becomes relative, it's situated, not just some global average.
And the emotional system, the limbic 2, is what balances that activation.
It's the homeostatic control. The geometry provides the structure of meaning, and the limbic 2 system provides the affective or emotional weighting for that meaning.
Which explains that diagram we saw of the dual space structure. You have two parallel spaces running at once.
Manifold A and manifold B. Manifold A is for the core thinking, the semantic cognition, and manifold B is just tracking the emotional and hormonal loads. It's the control layer.
So if things get too stressful or unstable on manifold B,
it can literally step in and divert the flow of reasoning on manifold A. It's a cognitive safety brake. It forces a switch from, say, creative, expansive thinking to a very constrained, cautious mode when the context demands it.
that structural design is just, it's incredibly impressive, especially when you remember their main claim is doing all this with smaller models. So let's talk efficiency. How do they pull it off without just adding a trillion more parameters?
Okay, so there are two main mechanisms. The first is phase 3, latent space injection. This is how they expand the model's capacity without actually making the model bigger. Instead of trying to bake all the world's knowledge into the model's static weights, which is hugely expensive,
Right.
they inject structured knowledge directly into the latent space, into its working memory, while it's running.
That's very clever. So the core model doesn't change, which saves on computation, but it can act like a much, much larger model because it has access to this real-time knowledge. But wait, if you're just injecting data directly into its work memory, how do you stop it from causing, massive confusion or even hallucinations? They're trying to build a stable system.
That's where the other layers come in. The injection is heavily, heavily mediated. The system only allows information that's contextually relevant and semantically aligned with the current state of the manifold. And if the emotional loads are screaming instability, the injection process itself gets throttled.
So it's like a dynamically regulated RG system, but it's all happening internally.
Exactly. Constantly refining its own context.
And the second efficiency mechanism, that was phase 4, the activation-based chain of thought.
Right. This is totally different from traditional chain of thought prompting, where you ask the model to literally write out its reasoning step by step. That's slow, it's expensive.
So if it's not writing it out, how does it review its own thinking?
The reasoning becomes a purely computational event. It's not text. The system looks at its own internal dynamics, the firing patterns in the neural network, to see which ideas, which semantic directions, are contributing the most to a decision. It then takes those key concepts and reintroduces them into its working context. It's a self-refining loop that happens at the speed of computation.
Which brings us to the big question of long-term learning, the catastrophic forgetting problem.
Yeah, a huge issue for traditional models.
Yeah.
If you try to fine-tune a massive model on new information, you risk it forgetting or degrading what it already knew.
So how do they solve that?
Phase 2, dynamic adapter structures. The approach is to freeze the base model so that the vast majority of the brain stays stable, but they insert these small learnable adapter modules in between some of the layers.
And these are tiny.
Tiny, maybe 0.1 to 2% of the total parameter count. And when new information comes in from a conversation, it gets consolidated into these adapters. So the model can actually retain new knowledge internally over time, kind of like how we consolidate memories.
So you're not retraining the whole brain every time it learns something. You're just updating these tiny specialized memory centers. Learning becomes a real internal update.
Yes. So to summarize the two really big ideas for you, the listener, the synthetic cortex reframes this whole game. It's not about scale anymore. It's about semantic geometry design and cognitive architecture. It's how you structure the thinking process.
And this isn't just a white paper. I mean, they're moving this from R&D into a real business. They're looking for partners, for investors, and they stress that because the architecture is always learning and adapting, it will never really be finished.
And that leads to the final provocative thought we wanted to leave you with. This architecture manages to separate analytical rigor from relational creativity. It puts them in different layers, and it uses these engineered emotional signals to decide when to flip the switch into that creative mode.
So what does that imply?
Well, if you can mathematically formalize and control things like creative leaps, logical stability, even cultural alignment, using just 13 variables in a defined geometry, what does that say about our own minds? It suggests that maybe the context and the regulation of thought are far more deterministic, far more engineered than we might like to think.